The Big Rip. Picture the fabric of space itself being shredded from the outside in. Galaxies first, then solar systems, then planets, then atoms. That is the Big Rip, and it hinges on one number, the equation of state of dark energy. If dark energy grows stronger over time instead of staying constant, expansion accelerates without limit. Every gravitational bond in the universe has a breaking point. Clusters of galaxies would fly apart roughly 200 million years before the end. The Milky Way dissolves 100,000 years later. Earth gets torn from the Sun about 2 months before the final moment. Then atoms themselves are pulled apart in the last fraction of a second. The universe does not explode. It simply comes undone, stitch by stitch, until nothing can hold anything together anymore. Vacuum decay. Somewhere in the universe right now, a bubble may have already formed. Physicists call it a false vacuum collapse, and the terrifying part is this. The Higgs field that gives particles their mass might not be in its lowest energy state. It might be sitting on a ledge. One quantum fluctuation could knock it off. When that happens, a bubble of true vacuum expands outward at the speed of light. Inside the bubble, the laws of physics are different. Atoms cannot form. Chemistry cannot happen. Life is impossible by definition. The bubble arrives with zero warning because nothing can outrun light. You would not see it coming. You would not feel it. The universe you know would simply be replaced instantly and completely by one where nothing like you could ever exist. Heat death. This one does not arrive in a flash. It arrives in silence, across a timescale so vast that the number of zeros in the years remaining would fill this script 1,000 times over. The second law of thermodynamics is the mechanism. Entropy always increases. Energy always spreads out. Stars exhaust their fuel. Black holes eventually evaporate through Hawking radiation. The last protons may decay after roughly 10 to the power of 40 years. What remains is a cold, dark, perfectly uniform sea of low-energy particles, with no gradients left to drive any process. No stars, no chemistry, no clocks, no difference between one region of space and another. The universe does not end with a bang. It ends by becoming perfectly, permanently still. The Big Crunch. Run the Big Bang in reverse and you get the Big Crunch. If the total mass-energy density of the universe is high enough, gravity eventually wins. Expansion slows, stops, and reverses. Galaxies begin falling back toward each other. The cosmic microwave background radiation, currently chilled to 2.7 Kelvin, starts heating up as space contracts. Stars collide. Galaxies merge into superstructures. The background radiation reaches room temperature, then oven temperature, then the surface temperature of a star. Every object in the universe is eventually cooked, then crushed, then compressed into a singularity of infinite density. Whether that singularity bounces into a new Big Bang or simply ends everything is a question physics cannot yet answer. Gamma-ray burst. This one is not hypothetical. It has already happened. Gamma-ray bursts are the most energetic explosions in the observable universe, releasing more energy in seconds than the Sun will emit across its entire 10 billion-year life. A long-duration burst from a collapsing hypernova within a few thousand light-years of Earth could strip away the ozone layer on the side facing the blast. Ultraviolet radiation would then sterilize exposed surfaces. Evidence suggests a gamma-ray burst may have triggered the Ordovician mass extinction roughly 450 million years ago, wiping out around 85% of species. The pivot is this: we would have no warning. Detection and impact would arrive simultaneously, both traveling at the speed of light. The universe does not need exotic physics to end life. It just needs one nearby dying star pointed in the wrong direction. Rogue black hole. Most black holes sit at the centers of galaxies, predictable and distant. But stellar mass black holes can be ejected from their home systems by gravitational kicks during formation, and they travel through the galaxy in silence. No light, no signal, no advance notice. A rogue black hole passing through the solar system would not need to swallow Earth directly. Its gravitational influence would be enough to destabilize planetary orbits. Earth could be flung into a wider orbit, triggering an ice age, or nudged inward toward the Sun, or ejected from the solar system entirely into interstellar space, where surface temperatures would eventually drop to near absolute zero. Astronomers have identified candidates, including one detected in 2022 using gravitational microlensing. The machine is already out there. It just has not found us yet. The Big Freeze variant. Separate from heat death, this scenario focuses on a specific acceleration. Observations from 1998, led by Saul Perlmutter and Brian Schmidt's teams, confirmed that the universe's expansion is not just continuing, but speeding up. If dark energy remains constant, the universe will expand until distant galaxies redshift beyond detectability. In roughly 2 trillion years, any civilization still alive will look out and see only their own galaxy. The rest of the universe will have crossed the cosmological horizon, moving away faster than light can bridge the gap. They will have no evidence that other galaxies ever existed. The observable universe will shrink to a lonely island. The cold will come slowly after that, not with violence, with isolation. Stellar collision cascade. In dense stellar environments like globular clusters, stars pass close enough to interact gravitationally. In a worst-case configuration near the galactic center, a chain reaction of close stellar encounters could destabilize multiple systems simultaneously. The Sun itself is not immune to stellar flybys over geological timescales. A passing star within roughly 0.8 light-years could perturb the Oort cloud, sending a barrage of comets inward toward the inner solar system. The late heavy bombardment, which scarred the Moon roughly 3.9 billion years ago, may have had a similar trigger. The cost is not instantaneous, it plays out over millions of years. But the mechanism is real, documented in the geological record, and requires no new physics whatsoever: proton decay. Everything solid you have ever touched might be temporary. The standard model of physics predicts that protons, the building blocks of atomic nuclei, could be unstable over vast timescales. Grand unified theories suggest protons decay after roughly 10 to the 34 years. Experiments like Super Kamiokande in Japan have searched for this decay without finding it yet, which pushes the lower bound on proton lifetime higher. But if protons do decay, all ordinary matter dissolves. Planets, moons, human bodies, every atom of hydrogen and oxygen and carbon, all of it eventually converts to positrons and pions and radiation. No explosion, no collision, just a slow, silent conversion of everything solid into light and particles, until the universe contains no matter at all. Magnetic monopole catastrophe. Paul Dirac predicted in 1931 that magnetic monopoles, particles with only one magnetic pole, should exist. Grand unified theories agree, and here is the dangerous part. If monopoles are real and abundant, they catalyze proton decay on contact. The Cabrera event of February 14, 1982, recorded a single candidate monopole signal at Stanford. It was never repeated, but if a flux of monopoles drifted through the universe in sufficient density, every proton they touched would decay instantly. Stars would dissolve from the inside. Planets would lose structural integrity. The machine requires only a particle that has never been conclusively observed. The fact that we have not confirmed monopoles does not mean they are not out there. It might mean we have not looked hard enough. Dark energy surge. The cosmological constant, the value Einstein called his greatest blunder, describes the energy density of empty space. Current measurements suggest it is small but positive, driving gentle acceleration. But some models allow it to change. If dark energy density spikes, the consequences are not gradual. A sudden surge would accelerate expansion so violently that the timeline of the Big Rip, normally projected billions of years away, could compress to a much shorter window. The physics of why dark energy has its current value is one of the deepest unsolved problems in science. The number we observe is roughly 120 orders of magnitude smaller than naive quantum field theory predicts. Nobody knows why. That gap in understanding is itself a warning. We are living inside a parameter we do not understand, and we are assuming it will stay stable. Boltzmann, brain apocalypse. This one starts with a thought experiment and ends somewhere deeply unsettling. Ludwig Boltzmann proposed in the late 1800s that random thermal fluctuations in a sufficiently large and old universe could spontaneously assemble complex structures, including brains with false memories. In a universe heading toward heat death, given infinite time, the probability of a random fluctuation assembling a conscious observer is non-zero. The disturbing implication is this: in a universe old and large enough, Boltzmann brains would vastly outnumber evolved observers. If you are statistically more likely to be a random fluctuation than a product of evolution, your memories, your history, your perception of a consistent universe could all be illusions assembled 1 second ago. The scenario does not destroy the universe physically. It destroys the certainty that the universe you perceive is real at all. Every one of these mechanisms is either grounded in confirmed physics or derived from frameworks physicists take seriously. That is what makes this list different from science fiction. The universe does not need a villain. It has its own termination conditions built into the laws that govern it. Some will arrive in fire, some in silence. Some will erase not just life, but the possibility of life, or even the coherence of matter. The question was never whether the universe ends. The question is which mechanism gets there first, and whether anything we could ever call intelligence will still be watching when it does.